Okay, hello everyone, my name is Alicia. Today we're going to be going through the Unit 4 revision for Specialist. So we're going to be prepping for your externals, going over all of the things that you may be forgotten since your last internal exam. I graduated last year too, so we're going to be going through all of my tips, what I did to do really well in Specialist, and everything that you could possibly need. Before we get started, if you have a look either beneath where you're watching, or if you scan this QR code, you can have a look at Slido, and on there I just like you guys to answer the poll and tell me how you're going in Year 12 Special so far, what you would want to do today. So we're going to be going over some content, obviously, and my tips, but if there's any specific tips or things that you'd like to do, or any particular maybe issues that you've been having in the last year that you wanted my advice on, just pop that in there and then we'll go through that today. And while you're typing that in there, I'll just let you guys know that this is one of the free ATAR Notes lectures that are offered for QCE students. ATAR Notes also has a bunch of study notes and lectures, and even the famous ATAR calculator. I know my friends and I would, every time we got a mark back onto the ATAR calculator and it tells you you're getting like a 99.9, you're like, woo, and then you don't get that. But yeah, ATAR calculator. And then there's also the other resources, which is TutorSmart. That is either private tutoring that you can get or classes every single week. And then we also have study guides, so that are the course notes with all of the notes for each of your subjects, and then the topic tests, which is like a big book of just a bunch of questions across all the topics, the whole syllabus, and a variety of simple familiar, complex familiar, complex unfamiliar. And then ED Unlimited, which is like a subscription service for all 6 of your subjects to access the resources for those. Okay, so before we get started, a little bit about me. I graduated from Boonesett High School. It's a little rural school in Queensland. I got an ATAR of 99.55. I'm now studying law and economics at UQ, which required an ATAR of 98, which is why I kind of had to grind so hard. And then in Year 12 Spec, I got an overall score of 96, 49 for my internal, and then I lost 3 marks for my external. So, before we get into the content, I'll just see if anybody has answered the poll. Yeah, okay. Okay, we will get right into the content then. So, for Unit 4, your 3 topics are integration, rates of change in differential equations, and stats. So today we're going to be going through those 3 topics, a brief overview, and then especially for integration, I'll go through all of the tips that I followed in Year 12. And after we've gone through all these topics as well, I'll tell you my studying methods, and especially my revision methods for the externals, because I obviously graduated last year, and how I managed to remember, a year's worth of content for all 6 of my subjects, with obviously the prerequisite knowledge from Year 11 and Year 10. And yeah, we'll go over that, and also some of the more, I guess, obscure things that I did, because I see a lot of things that students tell you, or, I guess studying guides and teachers tell you, are pretty basic. You've heard it all before, but I'll tell you the kind of, I guess, more weird things that I did that may or may not work for you. And then we'll also have, right about the middle, like a break time, and also at the end, like a question time where you guys can ask whatever questions you have, if there's any concerns that you're having so far, how you're going in the year so far, and like if there's any issues that you're having maybe in your exam which you wanted my advice on to fix up for your external, we can also go through that. I really just want to help you guys. As I said, we'll go through the content, but I know especially for the higher achieving students, this is just kind of a basic revision. You've probably gone through a lot of this stuff before, and like the base level revision is helpful, and just to have somebody explain it to you is helpful, but what you guys are really looking for are the more like micro tips and like the more so the advice on how to do well. So I'll sprinkle that throughout the lecture. We'll go through the basic concept, and then as an additional note, I'll give you my like tips for the really complex questions. Okay. Just a little bit of advice, and this stuff is pretty basic. Trying to understand the underlying theory, practice, and challenging questions. The main point out of all of these three is to study the challenging questions as soon, and this is one of my biggest tips, is as soon as you're comfortable with like the worked examples and the more simple questions, questions 1 and 2 from the textbook kind of thing, just do the challenging questions, because even if you don't know how to do it at first, if you struggle through it, and then even if you have to look at the answer online, you're still understanding the underlying concept behind the math far more than if you're just following like a formula. And I mean, psychological evidence shows that if you study the hard questions, you're way more engaged in what you're doing. You're not just kind of breezing through, and therefore you're learning more. I'll also get into that, and how to find those challenging questions, and which ones to pick, how you know which ones are actually relevant, which ones are just kind of a waste of time. I'll get into all that later. And on a similar note, studying for maths is all about practice. You need to do work consistently, even if it's just 20 minutes a day. That is hugely beneficial, and especially for your revising for exams. You need to be doing questions over and over again so that you can develop the muscle memory, and also identifying where you make mistakes. If you make notes of the mistakes that you commonly make, that is so helpful. The amount of times that I realize that I always forget the C at the end of indefinite integrals, or like always forget the pi outside of volumes of solids of revolution, that kind of thing, which I then avoided in the external because I had already in my mind that I knew that I usually made those mistakes and therefore was able to avoid them. And if you gradually start checking for those mistakes more and writing those mistakes down when you're studying, not just in your exams, you'll be a lot quicker at it, and then in your exam you won't spend so much time checking because you'll be so practiced at checking that you'll be able to do it quickly and more efficiently. So let's get started on integration. Basic things most of you guys probably already know, but the integrals tells you the area underneath a curve. So underneath the curve being the area between the curve and the x-axis. It is the opposite of differentiation. So when you are deriving a curve, you're finding the gradient, but if you get that derivative and you integrate it back up again, you're finding the area under that curve. The hardest part for integration in Spec, because in methods it's fairly straightforward, but in Specialist the hardest part isn't even knowing how to do all the methods, but it's knowing which methods to use, because there's so many of them. And often there's like multiple ways that you can do a question, and to do a question you're going to have to use like maybe 2 or 3 or even 4 or 5 different methods. So the hardest part is looking at what you have to integrate, identifying the patterns and the trends, and then subsequently identifying which method you need to use. So I'll go through all the methods now and briefly how to do them, just as a revision and to provide you guys with a like a simple, concrete definition of how to do them, just in case you're getting confused. But I will focus a lot on when to use each of them, because, as I said, it's really difficult, especially if you have a hard one, a hard integral, and you're looking at it and you know you're going to have to use like integration by parts, and there's like trig identities and different substitutions that you can do. It gets really complicated, and it's easy to start doing something and then just kind of like bark up the wrong tree. I don't know if that's the expression, but you know, to do something and then just get into a rabbit hole of doing the exact wrong thing and not getting any marks at all. I hate that. So we're going to go through how to look at the question and then just kind of immediately, or with minimal trial and error, know which method to go with. So the most basic concept for integration in Specialist is integration by linear substitution. So this is when you have a linear component within another function. So another way to identify this might be if you're looking at what you have to integrate, and you would derive it using the chain rule, and whatever's inside is a linear component. So for this first example here, integral of 1 on root 3x plus 1, we have a linear component, and we also have it within the other function, which is the third. So to derive that, I would use the chain rule with a power negative a half. And then for the second option here, you have a linear component within another function, being the squared, and I would also derive that using the chain rule. Or, I mean, alternatively, you could expand this instead of using linear substitution. It depends, but in general, this is a pretty simple example of when you would need to use linear substitution. So the steps are as follows. You firstly need to let the linear component equal u, and u represents the function. So it's not like a constant term. It's not like 3 or something like that. It's the actual function. And once we do that, we are going to derive u with respect to x. And what that means is we're going to find du dx. We're going to have u equals something, some function of x, and we're going to derive it like that u, it's just like function of x kind of thing. And then from there, we're going to isolate dx. And the reason we're going to isolate dx is because if you have a look at the two examples that we have up here, if we just sub the linear component for u, we're going to have an integral where we have something in terms of u, but we want to integrate it with respect to x. We might have 1 on root u dx, but we don't want to be integrating with respect to x, we want to be integrating with respect to u. So what we really need here is du. And the way to get du in there is to follow the second step, which is to derive u with respect to x, because then we can isolate dx and substitute that in, and we're then going to have something in terms of du, which is exactly what we want. I know when I first learned this, it kind of sounded like I don't know, breaking the rules of math. So I was like, oh, du and dx can't be separated. But I guess I learned that nothing is impossible. So the third step is to substitute everything into your original integral. So you're deriving something with u, with respect to u, and then we're going to integrate that with respect to u. So what that means is we're just going to like pretend that the u is an x and integrate it normally. And then after we've done that, we're going to have an integral only in terms of u. So what we need to do then to get it back in terms of x is just sub every single u that we see back for what we let equal u in the first place. So it's going to be some linear thing like, I don't know, x plus 2 or whatever we did. So as you can see, the primary goal of integration by substitution is where we can't integrate it by itself. We really just need to have a single function within the other function, because that allows us to integrate it. See, for our first example here, 1 on root 3x plus 1, we can't integrate that. We can't like separate the 3x plus 1 because it's under a third. We can't separate it. It's a plus, not a times. So what we need to do is get that to be a single function so that we can, you know, use the power and integrate it that way. So I'll get onto an example in a second, but before I do, I'll just quickly go over the tips down here, and these are for more complex questions, so these are for the higher achieving students. So the first tip I have there is if you have a linear component with an extra x. So in the example here, I have the x on root 3x plus 1, so we obviously have the linear component from the first example that I have up the top with an x on top. You have a linear component with an extra x. What you need to do, because, you know, obviously if you just sub u equals 3x plus 1, you'd still have an x there and a u, and you don't want that x. You only want everything in terms of u, but you still want to make that denominator a single term. You don't want the 3x plus 1, you want like a single thing, i.e. u. So we need to find some way of expressing x in terms of u. So what we need to do instead is rearrange what we have equaling u to isolate x. So in this case, we would have u equals 3x plus 1. What we need to do instead is isolate x using some simple algebra to get x is going to be a third u take 1. And once we've got that, we can then substitute this back in for x. So we would now have 1/3 u take 1 over root u du on 3. And from there, we can easily integrate that by just breaking up the numerator as you do in like a regular fraction. So we would just have that equaling 1/3 with u on root u, which you'd be able to just use index laws to get u to the power 1, and that's obviously u to the power half on the bottom using index laws, and then -1 on root u, etc., which you'd then be able to integrate fairly easily. If you guys have any more questions or you'd like me to go through that more in depth, just chuck that in the questions part of the slider, and we can go over it again later if you feel the need. I just wanted to quickly chuck that in there for the higher achieving students who weren't just, or like we're looking to do something a little bit harder. Okay, this is our example here. So, So let's start here. Our first step, remember, was letting u equal the linear component. So we would let u equal 3x plus 1. Our next step was to derive u with respect to x, giving us du dx. Using the power rule, the derivative of 3x is going to be just 3, because x here has a power of 1, so we'd go 1 times 3, and then the power of x is going to be 1, take 1, x to the power of 0 is 1. The derivative of 1 is going to be 0, because there's no x term there, and also because if you think about it, this is a vertical shift. The 1 is a vertical shift, it's a constant added to the end, and a vertical shift doesn't affect the gradient of the curve. So, our next step is to isolate dx. So I'm just going to quickly use the rule of 3 in algebra, which is basically where we're going to swap these two terms. If you haven't learned that before, the rule of 3, it is really useful. So maybe just like have a quick Google rule of 3 algebra, and it's really useful to know. So what that leaves us with is dx equals du on 3. And now our next step, if you remember, is we're going to sub in u and du on 3 into our original integral. So our integral, I, is going to equal 1 on root u du on 3. And we can integrate this pretty easily, obviously, because this is the same as u to the power negative a half with a 1/3 out the front, obviously, because that is a constant, so we can just take that out the front of the integral. And so that is going to be equal to 1/3 times 1 over 1/2 u to the power of a half plus c. So that's going to give us 2 and 3 root u plus c. And then we need to express this back in terms of x. So we're going to sub in 3x plus 1 for u again. So we're going to get 2 on 3, 3x plus 1 plus c, and that is our indefinite integral. So, if anybody had any troubles with that, again, just chuck your question in the question sections of the slider. I'll just have a quick look to see if anybody was having any trouble with anything. No. Okay. So, let's get on to integration with nonlinear substitution. So, we're going to use integration by nonlinear substitution when the derivative of u would cancel out any extra x's or any extra functions of x that you don't want. Because obviously you want your function, and in the end, to only be in terms of u. You don't want any x's, you don't want like x's in your what you're actually integrating, and you don't want a dx, you want a du. So you're going to have to pick something that would, the derivative would cancel out any extra x's or functions of x. So the most simple example of this is if you have two polynomial functions where one has a power higher than the other. So maybe you have something with x cubed and something with x squared. You would choose nonlinear substitution and choose that u equals x cubed, because the derivative of x cubed is something, some constant, times x squared, which would cancel out the other x squared that you don't want. So the two examples that we have here are x on root 3x squared plus 1. So in this case, we would let u equal 3x squared plus 1, because the derivative of that is going to be some term x, which would cancel out the x on the numerator up there. And if you also are particularly astute, you would notice that the derivative of 3x squared is just going to be one term, because that one has a a gradient of 0. So that would mean that it cancels really easily. If you had a longer polynomial with multiple terms in x, then it would be a little bit harder. The other example that we have is x cos x squared dx. So in this case again, we have one x term and one x squared term. One of the terms has a power that's higher than the other by 1, which means that the derivative of x squared is going to cancel out the x. The other cases other than polynomials in which we would use nonlinear substitution is if we have a product of cos and sine where neither has a power other than 1 obviously, or only one has a power, and the reason for that is because the derivative of cos is something sine and the derivative of sine is something cos, meaning that they cancel out. The other cases where we use it is for trig products where only one has a power other than 1. So one of the functions has a power that's not 1. And in that case, you let the one with the power that's not 1, say it's like to the power 4 or to the power 3 or whatever, you let that one equal u. For more complex questions, and this is a very specific tip, I'm just looking down the bottom, if you have a product of sec squared x and tan x to the power n, you need to make u tan x, because the derivative of tan is sec squared, so it cancels out. And that's a very specific tip, but just, I guess, for things to write down in your revision notes, I know the externals are coming up really quickly. For things like that, even if you don't have time maybe to practice those kinds of questions, if you can just remember that basic concept, if you get that on the exam, you'll know what to do. Okay, here is our example here. So, if anyone is up for it, you could tell me what our u is going to be in this case. So we have the integral of x multiplied by cos x squared. So remember, when we're doing nonlinear substitution, what we need to look for is making u the part of the function where the derivative of u would cancel out the extra x or the extra function of x that we don't want. So the question here is really, are we going to make u x or u cos x squared or x squared, or are you going to make it something else? Because sometimes, and I'll give you a hint, this is a more complex question, but sometimes you need to make u something that isn't even necessarily in the function, but that is some more complex questions. Yeah, so we do need to make u x squared, good job. So, if u is x squared, du dx is going to be 2x, and therefore dx is going to be du on 2x. Therefore, our integral is going to be x cos u multiplied by du onto x, and then these two x's that we don't want are going to cancel out. The integral of cos is sine, so we're going to have half sine u plus c, and then our last step, remember, is to substitute u back in, so that gives us half sine of x squared plus c. Okay, brilliant. So, our next step is integrals of trig functions. So these are our basic trig integrals. And then these are our basic trig identities. So the trig identities questions I tended to find not particularly hard, but it took a bit more time to learn how to recognize the patterns in what identities you need to use. And this goes for like the other topics in specialist, I know, because I obviously graduated last year. In last year's external, if some of you guys have done it, the last question in the tech-free test, you had to use a lot of trig identities. I can't remember if it was an integration question, but you had to use a couple of different trig identities. And I think the only reason that I was able to get the question was because I spent a decent amount of time studying how to recognize when to use different identities, because you've got to look for a certain pattern, and that's really the best advice I can give on knowing which ones to use, other than like practice and like making notes about, if you have this specific product, then you should do this. But you need to recognize the patterns, and especially if you know the identities really well, then it makes it easier. But you can also just recognize the patterns, make a list, and then go through the identities on your formula sheet, and that's pretty effective too. These are all on your formula sheet, by the way. You don't have to remember any of these, so don't stress. These are like some more specific tips that I had for trig identity integrating. They might be a little bit harder. In this lecture today, we're only doing a pretty simple question, and that's because it's, aimed at, the general audience. But these are like some more specific things to note down. Don't worry if you can't write these down all at once. The slides are available online, or you could just like snip the screen that I'm sharing right now and just paste on a Google Doc or something. But these were, if you have a single trig function squared, use a double angle identity. If you have a single trig function to an even power, use a double angle identity multiple times, and that's because double angle identities have squared in them. So you can use them multiple times. If you have a product of two different trig functions, double angle identities again. If you have a product where the two angles are different, so maybe you have sine of theta and cos of alpha, use a double angle identity, and then you can also use nonlinear substitution for that one. And if you have odd powers of sine and cos, like a product of sine and cos, and they have odd powers which are both other than 1, then you can use the main Pythagorean identity. So I guess for these tips, if you wanted to have a go at them, just like make a function, look through your textbook, or failing that, make a function following the guidelines, and then try integrating it and like graph on Desmos and see if you got it right. Okay, moving on. here is our example, and we've also introduced the definite integral, because when we're using substitution for definite integrals, there's just like one more thing that we have to consider, which is the fact that the limits here are for x, not for u. So you've just got to make sure that when you are substituting the limits in, it's for the function of x, not for the function of u. Or if you're going to do it for the function of u, you need to make these x limits applicable to a function of u. So, getting started here. So, what we're going to do here is we're going to utilize the trig function, or the trig identity, which is that sine squared x is equal to 1 take cos squared x. And what that allows us to do is cancel out the extra sign, which we'll get into. So, if we split this up and say that our integral is equal to 0 to sine x multiplied by sine squared x dx. So it's getting a bit messy already. And since we know that sine squared x is equal to what we have over here in the right-hand corner, that means that we have 0 to sine x 1 take cos squared x. And now if we remember from nonlinear substitution, if we have a sine and a cos, the pattern to remember is that the derivative of sine and cos cancel each other out. So if we let u equal cos x, and then obviously du dx is going to be negative sine x, dx is going to be negative 1 over sine x. And we can then substitute this into our integral. So I'll just make this into a box, not confusing. Our integral then is going to be equal to 0 to sine x 1 take u squared multiplied by, oh, I forgot to write the du there, sorry. The du outside of sine x. So obviously these two sine x's cancel out, just leaving us with that negative out the front. So we are now finding the integral of negative 1 plus u squared with respect to u, which is a lot simpler than what we initially had. And this gives us I'll just rub out this so we can keep working. So this then gives us the integral equals negative u plus 1/3 u cubed 2, 0. And what we need to be careful with here is that this 2 and 0, we can't just substrate in, because this 2 and 0 are for x, not for u. So what I would write here is 2 equals x, 0 equals x, just so that I don't forget. And then convert this back into x. So we're going to substitute u equals cos x again. So we're going to have negative cos x plus a third cos cubed x to 0. And then just getting this into our definite integral, we're going to get negative cos 2 plus a third cos cubed 2. And then cos of 0 for both of these is, cos of 0 is 1. So we're going to have negative 1 plus a third times 1 cubed, which is just 1. So we're going to get negative cos 2 plus a third cos 3 squared cubed 2. And then negative 1 plus 3 is going to be negative 2 on 3 times negative 1 again is going to be positive 2 on 3. Okay, I hope that sits well with everybody. I know that it was a little bit of a simpler example, but I would recommend for practicing harder questions where you need to recognize the patterns, go through the hardest questions that you could find from your textbook and from other textbooks and online, and you should be able to pick it up from there. So the next part is the integral of the log function. So obviously the derivative of ln x is 1 on x, and therefore the integral of 1 on x is ln x plus c. What some textbooks do is put, I just dropped my stylus, is put x in absolute value brackets. And the reason for that is because obviously you can't have ln of anything that's 0 or below. That's the reason they do that. So especially when you're doing word questions where the value, you know, the x might be graphing maybe time or the amount of water in a water tank or whatever, the value of that can't be below 0 or 0. So that's where the absolute brackets come in. For inverse trig derivatives, these ones are pretty straightforward too. The only thing, which I would practice specifically for with these is where you have to use linear substitution, because you might have, instead of the derivative of, instead of maybe integrating 1 on root 1 take x squared, it's 1 take 3x squared, or it might even be a whole linear function within the squared. I would practice those. So just some hints: if the integral is in the form of a on a squared plus x squared, you can use tan. Another helpful hint is if the numerator isn't actually a, it's something completely different. Remember, when you have an integral, you can take any constant out the front or take a constant from out the front and bring it back into the integral. So say you have, say a is 3, but you have 6 on the numerator, you can just take 2 out the front, leaving 3 on the top, and then you're all G. And then if your integral is in the form 1 on root a squared, take x squared, then use x equals a sine theta, and if the numerator is negative, then use a cos theta. Okay, getting on to partial fractions. So we're going to use partial fractions when the denominator can be factorized. So in the first example here, we have the denominator already in linear factors, and then in the numerator of the second example, we have something which is just a quadratic, which we would need to factorize to get into the 2 linear factors, and therefore to use partial fractions. So the thing to recognize about partial fractions questions is if you have an example where you have maybe a quadratic or a cubic even on the denominator, and even if it isn't in terms of x directly, maybe it is like a trig function, as in you might have like sine squared x plus 3 sine x plus 2. You need to recognize that that is still a quadratic, not entirely obviously because you've got the sine in there, but it's still a quadratic if you substitute sine for something else. So we'll get into an example of that in just a second. But my point is, recognize where there's a polynomial on the bottom, even if it's not directly in terms of x, because you might have to use partial fractions. So now getting on to the actual steps. The first step is to identify the 2 linear factors on the denominator. There might be more, in which case you should be able to find, I've only done for 2 linear factors here, but you should be able to find the formula for 3 on your textbook, or it's pretty intuitive to figure out. You're going to let that fraction be equal to a over one of your linear factors plus b over the other one of your linear factors. And then you're going to cross multiply, and also you're going to use simultaneous equations, which I forgot to mention, to find a and b. And once you've done that, you can integrate these 2 separate fractions, obviously using linear substitution if x has a coefficient other than 1. So the reason that we do partial fractions, I guess put simply, is because we can't just integrate these 2 examples up here. We can't just integrate by themselves. We have to make it simpler. It's the problem with integrating. It's not easy like deriving. So we need to separate things out, and all we're really doing is just kind of expressing it differently, algebraically, and that's, you know, we're not like doing anything special necessarily. We're just changing algebraically to make it easier to integrate. So in this example here, we have 28 divided by x plus 2 on x take 5. And what we're going to do is solve this, so that should be 28, is solve this by letting it equal to, as I said before, your a and b added with the 2 linear factors on the bottom. It doesn't matter which one is a and b, they both represent the same thing, as long as you don't mix them up when you're doing the working. So now we're going to use a little bit of cross multiplication to get our answer. So obviously it follows that we can then take this and this, we've done this before, which obviously gets us to a on x plus 2 plus b on x take 5 is equal to a x take 5 plus b x plus 2 all over x plus 2 x take 5. And what we can infer from that is obviously looking at the fact that this equation down here is equal to our initial... Oh, is this still working? Sorry guys, I'm not sure what's happening. Is it? Bear with me for a moment. Always having technological difficulties. I was sitting here for like 10 minutes before the lecture started because I was planning on using a different program to get my iPad to connect to my laptop, but it decided not to work. So I had to use Zoom, which is maybe why this isn't working. Okay, I'm not too sure why it's not working, but I guess the show must go on. So I will, while I'm trying to get this to work, take you guys through the tips that I had on my laptop, and then hopefully when it's started again we can finish off the example. So stop that. And so this is an example of what I was talking about before, where on the bottom we have a quadratic that is not directly in terms of x, so it's in terms of sine x. So in this case, if you have a think about it, what we need to do is recognize that there is a polynomial on the bottom which can be factorized. So we can factorize that, and after we recognize that, we also need to recognize that we have sine and cos, and as I said before, sine and cos cancel each other out, So if we use nonlinear substitution with u equals sine x, then the cos x on the top can be cancelled out too, and we can use partial fractions to finish that one off. And that question is from the Year 12 Specialist Jacaranda textbook, if you wanted to have a look at it and actually do it. Okay, now we are getting on to integration by parts. So this is kind of one of the more complex methods, not actually because it's hard to do, but because it's really easy to look at a question and think that what we need to do is integration by parts, but I feel like a lot of the time where I look at a question and think it's integration by parts, it's not integration by parts. I kind of just look at it and go, oh, it looks hard, it's probably integration by parts, but we have to be careful of that. What you need to look for with integration by parts, I mean, I guess generally, but this gets harder when you have to do integration by parts multiple times or you have to use different methods. But what you're looking for generally is where you have a product of two functions and the derivative of one of those functions would cancel the bad part, and by bad part I mean the part that includes the x you don't want because you want, or not even that, like the part that you wouldn't be able to integrate with would cancel the bad part of the integral of the other. So that sounds like a bit of a mouthful, but we'll get to it. The steps are, firstly, to assign each function as u or v dash, that should say, u or v dash, and after that we're going to derive u and integrate v dash so that we have both u, u dash, and v dash, and v to substitute into our formula, which you can see at the top. And then we're going to apply the formula. So after you've recognized that you need to use integration by parts, the next, I guess, like tricky part is identifying which part is going to be u and which part is going to be v dash. So what you need to look for here, especially on, exams where you're given the marking scheme, but also I guess in textbooks just by judging like how hard the question is going to be. If it's a low mark question or it's like a question at the beginning of the exercise, then you can usually guess that u is going to be the part that you wouldn't be expected to integrate, right? So if you maybe have a product of x ln x and you are asked to integrate x ln x, what you're probably going to do, I mean, this is just off the top of my head, but you're probably going to let u equal ln x because you need to derive u. You wouldn't really be expected to integrate ln x in that case, because integrating ln x requires integration by parts within itself, and if it's an easy question, you're not going to be expected to do integration by parts twice. However, in saying that, if you have a more complex question, maybe it's worth like 6 marks or something like that, then really anything is possible, and you just need to like recognize the patterns, which you'll get better at with practice. So our example here is x cos x. Now I'll just quickly see if I can get my iPad to screen share again, but if we can't, then I guess I'll just have to talk through it with you guys. So just bear with me for a second. I don't know if this is going to work. Okay, I can't get this to work, it seems. So, we will just I'm so sorry for the technical difficulties, guys. I'm not sure what is going on with everything today. Okay, well, in that case, what I'm going to do is briefly explain this to you guys and maybe try to write it out with my laptop if I can. So, in this case, what we need to think about for identifying u and v dash is that u needs to be the function that either the derivative would cancel out something that we don't want from the integral, or the derivative is going to get rid of any x's at all. So, in this case, we're going to let u equal x. And the reason for that is because the derivative of x is going to be 1, which means when we're subbing this into the formula, we're going to have something where we don't have a product of two functions, because we're just going to have 1 times something, and that's exactly what we want. In cases where you have maybe where you have like e to the x, obviously the derivative of an integral of e to the x is always just e to the x. So those ones, there's a little bit of a knack to, which I'll get to in the next slide. But for this one, we're going to go, and we'll see if this works, u equals x, and therefore u dash is going to be 1, and then therefore our v dash is going to be cos x and therefore our v, by integrating that, is going to be sine x. It's very slow. X. So by using our formula, we're going to get that our integral is going to be equal to, and I won't write this out because it'll take too long, but x sine x minus the integral of u dash v, and u dash v in this case is going to be 1 times sine x, and as I said, we're just going to be left with 1 times some function, which is exactly what we want, because now we don't have a product of two functions, we just have like one function by itself, which we can easily integrate. So if you're doing this at home, just listen now because I'll tell you the answer. We're going to be left with the integral being x sine x plus cos x plus c. Okay. Now here are my tips for the complex questions. So these are for more so for the higher achieving students. So you may need to use integration by parts multiple times. So this usually occurs when you maybe have causes and sines, because you can collect like terms, and also with e to the x. But I think we'll get into that in the next slide. So for example, with the integral of x squared cos x up here, if u equals x squared, you would still be left with 2x cos x as something that you need to integrate. However, this 2x cos x, we can actually use integration by parts again and let u equal 2x, because in that case we're doing something very similar to what we did in the example that we just did, where the derivative of 2x is just 2. You don't have any x's in it, which means in your final integral you're just going to have a trig function without any product with x, which is really easy to integrate, and that's exactly what you want. So the point of this, that dot point there, is if you have a product with like a smaller polynomial, maybe such as like x squared or x cubed, as a product with some other function, you can use integration by parts multiple times by letting u equal the polynomial part. Yeah, the only tricky part with that is it gets kind of long, so you don't want to make any like small mistakes or like run out of paper on your page and have to like go down to the next line, stuff like that. But just try to be neat, and it should be all good, and you shouldn't make too many mistakes, hopefully. Yeah, so if you make u the polynomial part, etc., 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 that's just what I've written there. And similarly, if you make u the function to a power, it will eventually derive down to just the function to the power 1. And I said this before, but if it doesn't make sense for them to expect you to integrate a function, so maybe if you had like ln x or some complicated, maybe if they were asking you to integrate a product of sec x and something else where you don't have a formula for the integration of sec x, then the sec x is probably going to be a u, because you do have a formula to derive that. Okay. My other very specific tip, and this is also an example, which I'm glad I wrote out. Apparently my iPad isn't working. So if you have an integral with a trig function multiplied by another function, not necessarily a polynomial, because we just did that before, but if it's multiplied by maybe specifically an exponential, because exponential, the derivative and integral is always the same, then you can keep integrating by parts until you get two like terms with the integral that you wanted. So in this example below, we have, or we're trying to find the integral of e to the x cos 2x. So in this case, at first you might look at it and go, well, you know, the e to the x is no point, because regardless of if I derive or integrate that, you're still going to get e to the x. It doesn't really help. Cos 2x, you're just going to alternate between sine and cos and sine and cos and sine and cos again, so it seems kind of pointless. But what you need to do in these situations is let u equal e to the x, because cos and sine are going to cycle around, so you can just collect like terms. So by letting u equal x and doing integration by parts one time, we're going to get this part down here, e to the x cos 2x integral is equal to e to the x on 2 sine 2x, take a half of the integral of e to the x sine 2x. And if we integrate the second term by parts again, we can get something which is the integral of e to the x cos 2x, which is exactly what we're trying to find. So if you look at this last equation here, we have the integral of e to the x cos 2x on the left-hand side, and we have another term of e to the x cos 2x on the right-hand side. So we can just pretend they're like, you know, a whatever. Take that negative a quarter integral e to the x cos 2x onto the left-hand side, collect them as like terms, and end up with the integral that we wanted. I would write that out for you, but I can't. Okay, now we're getting on to areas between curves. So, areas between curves is just integration with an extra step. Instead of just finding the area underneath a curve, we're more so finding the area underneath each separate curve and then finding the difference between that. So we'll be given two curves. You might be asked to draw the graphs out. And the reason for that is because you need to be aware of the intercepts. So the biggest mistake that I would make with areas between curves was I would completely neglect the intercepts, because depending on how much you remember from this year, when you find the areas between the curves, you need to separate the integrals depending on the intercepts, because every time the function which is on the bottom or on the top changes, you need to either switch the limits or switch the sign of the integral itself. So make sure you draw your graph out, make sure you find your intercepts, and check whether those intercepts are within the domain that you've been asked to find the area of. And then, go function, the top function, which is the function, like furthest away from the x-axis, take the bottom function, which is the function closest to the x-axis, and then integrate that as before. So, the next topic is the volumes of solids of revolution. So, those two formulas there for if the volume of solid of revolution is rotated around the x-axis or the y-axis are on your formula sheet, so you don't need to worry about that. A and B are the limits, the 2 points between which we're calculating the volume, and my biggest tip here, in all caps, is to check if it's rotated around the x or y axis. Many times it said it rotated around the y axis, and then I just completely disregarded that and went, oh, it's rotated around the x axis. No, it's not. No, it's not. And my other tip is to make sure you remember the pi. So the pi is like the constant. I find it really easy to forget the pi because I was so concerned about the other things. Make sure in your external you have a look over the formula again and check that you haven't forgotten the pi and that you've rotated around the right axis. Another tip for more complex questions is if it is a symmetrical relation, you can cut it up so that one of your limits is 0, which makes the whole process a lot easier. So what I'm talking about here is if you needed to find the volume of a sphere that was centered at the origin, instead of making your limits, maybe if you're rotating around the y-axis, instead of making your limits the two y-intercepts of the circle, what you can do instead is only use the quarter of the circle which is above the x-axis, and then multiply that whole volume by 2. And that means that one of your limits can be 0, which really makes the process a lot easier, especially in the exam when you're kind of under a time constraint. Again, I would draw a diagram, but she's not working. So in this example, we are finding the volume of a solid rotated around the x-axis with y equals root x plus 6. So what we would need to do here is, using the formula, go v equals, we need to remember the pi out the front, pi. Our two limits are going to be negative 6. I don't know what happened with the 6 there. 6 and 0. And then if we have a look previously, when we are rotating something around the x-axis, we need to have the function as y squared, which means the function needs to be in terms of x. So we're going to have root x plus 6 squared. Obviously, the square root squared part cancels out, so we're just going to be going x plus 6 dx. And I won't go through the rest of it, obviously, because it would take too long, and it would be too messy for you to read anyway. But from there, we will just integrate it normally, definite integral. And then the thing to remember at the end is to make sure that you remember to write squared units. You're not given any units for this one, but as it is a volume, cube units, as it is a volume, you need to write cube units, otherwise you might lose marks for forgetting the units. Okay, next we are getting onto Simpson's rule. So Simpson's rule is a method of approximating the area under the curve. It is a little bit similar to the rule that we use in methods with all the different, I can't remember what it's called, but all the different shapes underneath the curve. It's a little bit similar in the sense that we're approximating the area under the curve. And the question that you're most likely going to be asked on your external about Simpson's rule is either like a multiple choice, or you might be asked to find the area under the curve using Simpson's rule and then check the reasonability of your answer by using definite integrals. So in that case, what you need to do is use the function that they've given you and find the limits for Simpson's rule using that function by cutting it up into however many strips you need. And then once you've done that, just integrate the function and find the definite integral as per usual, and you can therefore say that the solution is reasonable because you verified it using definite integrals. Maybe it's vice versa. As a general tip, it is a part of the syllabus that says you need to check the reasonability of your results. So if an exam question ever asks you to check if your result is reasonable or explain the reasonableness of your results, what you need to do is kind of either find a similar or the same answer using different maths. So that's what we did in that question. We used Simpson's rule and definite integrals to get a similar answer. Or you might have to explain why your answer makes sense. So a lot of the times I see that in maybe dominance matrix questions, which I think was from a while ago now. But if you use dominance matrices to find that, a certain result, you would need to explain why that was reasonable given your information. Okay. Anyway, Simpson's rule is pretty easy to use, pretty straightforward. The only tricky thing is that it gets quite long. So the most important thing to remember is to make sure you're following the formula and that you're not writing anything too messily, because then you might run out of room and get really confused. So the number outside of the whole big brackets is going to be the entire width of your domain, which is going to be like the difference between the two limits, b take a, divided by the number of strips. So they're going to tell you find the area under this function with maybe 5 strips or something like that. And then that's your n. And then your values within the brackets are obviously x, not x of 0, but like the initial term, and then the last term is at the end, and then all the in-between ones in the middle. So, technology for Simpson's rule is basically just using your calculator to add it all up, / using the table function in your graphics calculator to find all the values of a function. So, next we are getting onto the probability density function. So, in methods, we have done these with all different types of functions, but in Specialist, we only focus on the exponential one. So this one you'll be given for word questions. Although I think in one of the previous exams, or one of the mock exams, you did have to integrate this, but this is obviously something that you can integrate with relative ease. So this function shows the probability of an event occurring within some time interval, and the lambda is frequency of occurrences, which like is an indicator of how often the event occurs, and then obviously the frequency is the reciprocal of the mean, or is inversely proportional to the mean. So if an event happens very often, then the mean time for it happening is shorter because, you know, it happens more times, so it takes less time for each one to happen, if that makes sense. So this is a simple example of the probability density function for exponentials, where lambda is 0.25. And the area under the curve we need to calculate using the probability density function and definite integrals. And the tricky part, I guess, is that the function obviously has a horizontal asymptote, but that doesn't mean that the area under the function itself is infinite. It just means that we need to consider the limit of e to the x, which we'll get into. So, you just need to apply it to simple situations. Just make sure you're not messing up mean and frequency. That's a common mistake. And remember that if one of your limits is infinity, e to the infinity equals 0, or can be approximated as 0. So, in the example that we had before, maybe your limit is going to be what is the probability of an event occurring, you know, after 10, so you want this area here. So your limit is going to be 10 and infinity. So don't just, you know, stare at e to the infinity, or what even is that? E to the infinity can just be approximated as 0, and that's really useful on tech-free tests too. So, CDF, or the cumulative density functions, are a bit of a tricky concept. We don't really go over them as much in methods, so a lot of students tend to forget. But the CDF is the integral of a PDF. So instead of the probability of something occurring being the area underneath the curve, the probability of something occurring is actually just described by the y values on the curve. So, the probability, the CDF for our PDF before is 1 take e to the negative lambda x, and we can then use that to calculate probabilities of things occurring. However, I wouldn't worry too much about CDF for Specialist. I think it's mostly focused on the PDFs. I've never come across a question in Specialist about CDFs for exponential functions. So I'll just focus on those, but do a couple CDF questions if you want to be extra prepared. Okay, next we have quantiles. So, quantiles are a way of describing, the statistical, or like what group a statistic falls into. So, if you have it's just kind of another way of expressing the probability of something happening. So the 20th percentile is going to be further away than, say, like the first percentile, that kind of thing. So a summary of all of this is integration, practice the general principles, and also get onto the hard questions. Integration by substitution, remember to change the bounds. You're not going to mix up u and x. Areas under curves and volumes, draw out the curves. Make sure that you're not missing any intersections. If you have a PDF, make sure you understand the formula. Don't mix up mean and frequency. And then, in general, just practice and remember the plus C for your indifferent integrals. Okay, we do have a set of questions here. I obviously can't take you through them, which I'm very sorry for. But if you do want to attempt them, the slides are available on the website, and the answers are also on the slides too. So that should help you with that. Okay, now we are getting onto implicit differentiation. So implicit differentiation is when we have a function that is not just in terms of y being isolated on one side and lots of x things on one side, or vice versa. Implicit differentiation is when we have y's and x's all mixed up and we can't really separate anything out just to differentiate it all with respect to one thing. So what we need to do in this case is use the chain product and quotient rule to derive even the y terms with respect to x. So in this case here, if we were finding dy dx, obviously if you remember when we are deriving separate terms, the derivative of the whole equation is going to be, the addition of the derivative of each different term. So we can go d dx of x squared plus d dx of y squared equals d dx of 4. So the derivative of x squared with respect to x is nothing we haven't done before. It's just 2x. However, the derivative of y squared with respect to x is a little bit trickier, obviously, because we don't have any x's in there. So what we need to think about is using the chain rule. If we let y squared equal, I don't know what happened with that equal sign, but that is an equal sign, everybody. If we let y squared equals u, and we find du dx, du dx, then that is going to be, du dy. We derive that with respect to y, then that is going to be 2y. And now, if anybody remembers implicit differentiation, maybe think about what we're going to do next. So we need to get something including dy dx. So we need to go du dy multiplied by dy dx is going to give us du dx, right? Which is what we want, because these two dy's on the numerator and on the denominator are going to cancel out. So that gives us du dx, which is what we want to be adding in, because we want to be deriving this, we're deriving u with respect to x. So that means that du dx is equal to du dy times dy dx, which is, as we've calculated before, 2y times dy dx. So over here we're going to have 2y multiplied by dy dx. And if you are familiar with these questions, you'll recognize that what we're really kind of doing is just deriving the y term with respect to y, just like pretending that it's whatever, just deriving with respect to y, and then chucking a dy dx at the end, which is like an easy shortcut once you get used to it. And then obviously the derivative of 4 with respect to x is 0. And from there, to find dy dx, what we actually need to do is do some algebra and isolate dy dx. So I won't write it because it'll take too long, but what we need to do is take this 2x over to the other side to give us negative 2x, and then obviously this 2y is multiplied by dy dx, so we're going to go negative 2x divided by 2y is going to give us dy dx. Those 2's are going to cancel out, meaning that dy dx is going to be negative y on x. So again, the general steps are you need to derive each term with respect to x, whether you're using the chain rule, the product rule, the quotient rule, whatever, to achieve that. And then you need to isolate the dy dx. In more complex cases, you might get a few different dy dx's, and in that case, you need to factorize out dy dx so that you can then take all those terms you factored out over to the other side by themselves, leaving dy dx on one side. So next, we will get onto related rates and chain rule. So related rates are used when we need to find 2 or more variables that are related to a common variable. So most of the time we need to use implicit differentiation and then sub in the given numbers. And our related rates are, I feel like, one of the most enjoyable topics of specialists. I always find it really fun to come up with all the different equations, kind of like optimization, where you need to like play around with different formulas and concepts and stuff. I really love related rates. So generally what you need to do is write down any related formulas from your formula sheet, whether that's like volume or area or whatever. And you might also need to write down any properties of the shapes you're working with. So one of the most common ones for related rates is similar triangles, which I would really recommend studying a little bit. They also come up in optimization methods. I know in last year's external there was a question where you needed to, where similar triangles was used. They told you, but I mean, expect the unexpected. It's QCEE, so make sure you study up on related rates. There should be a few worked examples in various textbooks on those. We won't go over any of the related rates questions. Right now there is a question at the end. Again, I can't do that for you guys, but yeah, if you do the question at the end and then have a look at the answers, which are all on the website, then you should be good. So this is solving derivative equations in the form either f of x or g of y. So in f of x, pretty simple. G of y is a little bit different because remember we want to be integrating with respect to y, but all we need to do is rearrange and make y the subject, but the second one might take a little bit longer. Separation of variables is really useful, and you typically see this when you are doing questions. I see it with questions about like the absorption of medicine in the body and stuff like that. But it's basically where you have a function in terms of both x and y, and it's not complex to the point where you need to use, or rather, it is like a product of some sort. So you might have, only x is in the top and y is in the bottom, or maybe some function of x multiplied by some function of y, something like that, and you just need to get all of the y stuff on one side, so all the y parts of the function and the dy on one side, and then all of the x parts and the dx on the other side, and then you're just going to integrate those. So one side is going to be integrated with respect to y, and the other side is going to be integrated with respect to x. So once you've done that, once you've integrated it, you usually simplify it and make y the subject. If you're doing a word question, what you're going to need to do is make sure you're including the initial condition, which is if they give you some sort of coordinate, maybe the initial value is 1, or the initial value is 0, or something like that. And you'll need to find the C value, because you can't forget the C value with these ones. Even though you're integrating on both sides, make sure you still remember the C. Okay, so slope fields are a graphical representation of of derivative equations. So I remember the first time I saw slope fields, I was like, what even are those? I don't like the look of those, and I don't want to do them, but they're actually not that hard. So basically, each short line segment represents the slope of a tangent to the curve at each given point. And what we need to do to make a slope field is make a table of values. So here we have what a slope field would actually look like. And so what we need to do to achieve this is we need to make a table of values with the x and y coordinates along the top, and then the derivative at that point along the bottom. So we might even have to use maybe implicit differentiation to get to the derivative function, and then your derivative is going to be dependent on both x and y, so it even might be a little bit more complex. But the tips for these is, I guess, to remember when the derivative is 0, you're just going to have flat lines, stuff like that. It doesn't really matter how super accurate it is. Just make sure that it all looks like you understand. And another thing to take note of is you can see along here the x-axis, there are no slope lines, which implies that maybe at that point the function is discontinuous, or the gradient is discontinuous. And this would happen if maybe we had our derivative function dy dx being like x on y, then at a particular y value the function can't exist. So tips for when you're going the other way and you're given a slope field and you need to come up with the function. You'll usually be given these for multiple choice questions. It's not too difficult. I think in some of the previous externals what was given is like a slope field and then 4 different functions, and then you need to figure out which slope field, which function matched the slope field. So for those ones, the most important thing to remember is like where the line segments are horizontal and vertical, and where the gradient is positive and negative is another helpful thing. But other than that, it's kind of process of elimination. You go through and go like, well, maybe that one can't work because the function is discontinuous at that point and the slope field doesn't represent that, so that one's out, and then going through like that. Okay, moving on to logistic growth. So exponential growth kind of assumes an indefinite growth of one variable, but logistic growth considers a restriction on how fast the growth could be, or like the limit of how fast the growth could be. So in logistic growth we have something called carrying capacity, and that is kind of like the maximum value reached. So maybe you have a zoo of monkeys, and we can never have more than 20 monkeys or something like that. Anything like that where there's only a certain amount of a population or of a something that can be achieved. So this is the derivative equation, but the logistic growth curve and the actual equation you'll most likely use is this one. I don't think this is on the formula sheet, so you might have to remember this one. But as you can see here, the exponential function just increases indefinitely, but the logistic function reaches a horizontal asymptote, which is its carrying capacity. So, a summary. For implicit differentiation, we use when we can't make y the subject of an equation. There's too many x's and y's mixed up in everything. We're going to use the chain product and quotient rules as required for implicit differentiation, and then we're going to make dy dx a subject. We're going to isolate that. We might even need to use factorization to factorize out dy dx. Related rates is just an application of the chain rule. In general, you just need to remember any relevant formulas from your formula sheet, or similar triangles, or any other like properties of the shape that you're working with. And then you need to work out like what you don't know, how it's related to what you know using the chain rule. Separation of variables you need to use when you have like a product, where you have like a product of something, some function of x, and then some function of y, and you're just going to take all of the x's, including the dx, onto one side, and all of the y's, including the dy, onto the other side. And then you're going to integrate both sides with respect to either x or y, depending. The slope fields, you need to make a table of values with the x and y and the derivative function, and then look for like the giveaway points, which is where the line segment is horizontal or vertical, or maybe where there's no line segments at all, so it's discontinuous. Logistic equations, you just need to apply the formula as needed. I don't think those ones are too hard. It's mostly just applying the formula. Okay, now we have a bit of a break, which is very late, which I apologize for. We had a lot to get through. But if anybody has any questions about studying Year 12, anything related to externals, feel free to chuck them in the slider. There should be a page for you to put questions in anonymously, and I'll go through and answer them. If everybody's too shy, I'll just give a brief overview of some of my tips for Year 12 and externals while everybody's taking a break. So, discard those. Okay, so I don't have any questions. So, really quickly, I just wanted to give some brief tips on Year 12 and especially for externals because they're coming up pretty quickly. So for revising for externals, I know everybody has 5 or 6 subjects. You want to balance the time between them evenly. It's really hard. You're getting stressed. There's a lot of pressure for externals, so I know it can be hard. But what I would recommend doing, if you're behind, then what I recommend doing is going through a couple of topics each day for each subject, doing the worked examples, and then in a week or so going back to those and without looking at your notes do some more questions, and just try to get through all of the content. If you're already kind of on top of things, you're feeling like decently confident, then what I'd recommend for you is to go through and revise. Look through the worked examples. If you think you're okay with the worked examples, then go through and do the hardest questions you can find. You learn the most effectively when you're doing hard questions, and that's when you really understand the concepts. So if you're up to it, do the hard questions, smash through those. If you have like a decent chunk of time, you're not like working or anything before your externals, I'll quickly show you the notes that I had for my specialist externals, just in case, for some inspiration. So these are the notes that I had for my specialist external. As you can see, it was just a massive document. Each syllabus dot point are in these bold green, and it's got bold green writing. And by doing that, I made sure that I didn't miss any syllabus dot points, because I know even in last year's external, they included some really big questions. There was like a 6-mark question on like matrix algebra, and like nobody cares about matrix algebra, but I was only able to like get through it because I'd made sure that I'd done everything for every single syllabus dot point. The other benefit of this is that you can write down the formulas that aren't on your formula sheet and make sure you remember them. It really sucks to know all the hard stuff but then forget something really simple. So equation of a sphere, midpoint, equation of a straight line, all that kind of stuff. The other thing that really helped is when I would go through the hard questions, I'd write down any strategies that I came up with, regardless of how kind of like specific they were to that question. But I'd write any tips down, and anything like that. I think I even had like a whole document just about integration. So that really helps if you write down the mistakes that you commonly make. That's also so helpful. especially if you're one who is like more of a high achiever, so you understand all the content and you can do all the complex and familiar questions, but you just like lose so many marks from making small mistakes. That's so frustrating. So make a list of the small mistakes that you make. I know, if you always forget the C for indefinite integrals, or you always forget the pi for volumes of solids of revolution kind of thing. So make sure you make a list of those, and then in your exam, you're kind of mentally checking, like, have I got the C, have I got the pi, kind of thing. And that really helps you to avoid making those mistakes, which is, like, so annoying. The other thing that I would recommend is just making sure that you are looking after your physical health. I don't mean to like an insane degree, but it helps your brain, obviously, if you're like relatively active and you eat well and that kind of stuff. And make sure you sleep enough. I know it's really tempting to spend time studying instead of sleeping. No, don't do that. You can't remember anything if you don't sleep. The best idea, I guess, it might be a little bit late for some people because externals are coming up, but the best strategy is to do the work consistently, and then you don't have to cram, and then you don't lose sleep, and then it's all just in your brain, ready, and you don't have to cram it all with complex unfamiliar questions. Then make sure you practice a lot of those so you actually understand the concept. And if you can, practice them consistently, don't just cram, and then that's how you really do well. Okay. Before we get back into the content, I'll just show you guys the offer that ATAR Notes currently has for the bookshop. So we have course notes and topic tests. Depending on your situation right now, the course notes are good if you're behind and you just need to revise everything. I found them really helpful to study for throughout the year, but they're also really good for, right before externals. They're written in a really, digestible tone. It's not like a textbook where it's written by, like, some really, really old guy. It's, written by, like, 19-year-olds. It's really understandable. It's in a casual tone. They're all previous graduates. The authors are, so they all know, like, the syllabus and how to actually do well on QCEE, obviously, because older people just telling you how to do well isn't necessarily that effective because they've never been through it. And then the topic tests are just like a really big book of questions. I would recommend those for revising. If you're already kind of on top of the content, just go through that book like 3 times or something like that, and that will really help you. And then we have 15% off on those if you use the code 15SEP at checkout. We also have the text guides, so those are for English and literature. So if, I used the text guides indirectly. My teacher had ours for Hamlet, and then she'd tell us like the important parts of it. It was really helpful. It goes through all of the criteria. There's like practice essays, practice questions, example essays, the synopsis of the play or book, and then all of the, the attitudes, values, and beliefs, and the language features, and analysis of the quotes, and all that kind of stuff. I found it really, really useful, and I ended up getting a 24 out of 25 on my English external, so they're really good. And then we also have Ed Unlimited, which is a subscription service where you can access all of the course notes and study guides for all 6 of your subjects online. And then you can get 21 days free with my code AliciaQCE, which I would really recommend, especially because it's coming up to externals, even if you don't actually end up paying for the service, if you just use it for the 21 days. It's really, really helpful. I had all the course notes for my STEM subjects, and it was really good. Okay. Now we are getting on to modeling motion. We're going to have to go through this a little bit fast because we only have 35 minutes left. So we're going to go through modeling motion. These are our definitions for acceleration and velocity. These are on your formula sheet, so don't stress about remembering them. We'll come back to these a little bit later on, because I know it's kind of tricky sometimes to know which acceleration formula to use. But momentum is essentially mass multiplied by velocity, and the rate of force is the rate of change of momentum in a system. And therefore, force is equal to mass times acceleration. That's a really important one to remember for the motion questions. So, action and reaction forces are a point on your syllabus. An action force is, the force of one particle on another. Maybe you're pushing a door open. And the reaction is when the second particle exerts an equal and opposite force on the first. So what that means is that if you push the door open, the door kind of pushes on you with the exact same force in the exact opposite direction. A great example of this is if you are an astronaut in space. I think this was something that actually happened. An astronaut was in space and he was tethered to the spaceship and went to I think get back in the spaceship and climb back in. And he went to touch the spaceship and he just absolutely bounced off. And it was because when he touched the spaceship exerted an equal and opposite force on him, but because he had a smaller mass, he moved a really long way, but the spaceship, because it was so massive, didn't really move that much at all. Okay. The common reaction forces that you might encounter is tension and normal force. Those are the kind of forces you're going to be asked to calculate for these questions. Concurrent forces is also a dot point on your syllabus. So that's when there's multiple forces acting on an object, and they're all in different directions, and it's a little bit confusing. So for example, if two people are pulling on a rock and both people exert a force of 1,000 newtons, but person A pulls to the right and person B pulls upwards, so we have one right and one upwards. And then we need to find the net force, which is going to be this line here. So if we have one going to the right and one upwards, then the net force is going to be this one here. And then we usually just need to use some sort of trig or something like that to figure out that vector. This is a harder example. So this is if we have a mass of 2 kilos rolling down a ramp, and we need to find the force in terms of mu, so that the object can stay at rest on the ramp or move up at a constant velocity. So we can obviously see here that this ramp is inclined at 30 degrees, and that the force that is force exerted on the ball that is pulling it down is mg, mass by gravity. The normal force is exerted perpendicular to the plane, and then the force pulling it up the plane and the friction on the mass is pulling it down the plane. So in these cases, what we need to do is, instead of just leaving our axes like this, where we'd have to alter a lot of things, it's actually easier to rotate the axes like we have on the right hand side here. And what we're doing then is rotating the x-axis so that it's like parallel to the plane. I won't be able to figure out this question for you guys. I'm so sorry about this. But if you did want to find out the answer to this question, it is in the ATAR Notes course notes for Specialist Maths. Okay, so the general rules for concurrent forces is to always draw a diagram and label all the forces with the directions and angles. If it's a flat surface, you don't need to worry about changing the orientation, but if it's on a ramp, make sure that you change the orientation of the x-axis to be parallel to the ramp, and that just makes everything a lot easier. So, when you have non-constant forces, this is when we need to use the different acceleration formulas and velocity formulas given to you in the formula sheet. So, if you're given A in terms of x, you're probably going to have to use this formula here. And if you're given A in terms of v, you're going to have to use this one over here to get x as a function of v. And then you're going to have to solve using derivative equations. Okay, simple harmonic motion. So simple harmonic motion is kind of a trickier concept to get your head around. It occurs when you have motion which is like cyclical, right? So it's moving back and forth. So maybe instead of an object being just thrown upwards, it is a pendulum or a spring, like, you know, moving back and forth, or something like that. And the reason for that is obviously because simple harmonic motion is modeled using sine and cos functions. So it has like that wave-like nature. The acceleration is always proportional to the displacement, but it's opposite in direction. These kinds of things are useful to remember, just as like little tricks for your questions. And as a result, the further away that the object is from the center, the greater the tendency is for the object to return to the center. And the reason for that is, you know, if you have a pendulum and it is moving back and forth, it's getting, you know, the further it gets away from the center, the slower and slower it's getting, right? It's getting slower and slower and slower because it's being pulled back down to the center. But as it's moving back to the center, it's getting faster and faster and faster. What that also implies then is that the, you know, the velocity is the greatest in the middle. Simple harmonic motion has endpoints of motion, which we'll call A and negative A. We don't need to derive it because it is on the formula sheet, so we'll skip over that. And then these are the variables in the equation. So our V is velocity, our omega, or like the W kind of looking thing, is angular velocity, which is measured in radians per second. A is the amplitude, or the end point. So obviously, the end point is going to be some distance away from the equilibrium, which is going to be the amplitude. And then the x is the displacement at a given time. Looking at these next formulas here, for x, this obviously just follows the general form of sine and cos functions, where we have the dilation factor being the angular velocity, and then we have the phase shifts being alpha and beta. The other thing that you need to remember, which is also on the formula sheet, is that the period is equal to 2 pi on the angular velocity, and the frequency is directly inversely proportional to the period. And that's because, you know, if the period is longer, if it takes longer for something to occur, then it's going to happen less times, in a given amount of time. So my general tips for these questions is because, what usually happens is you're given a set of information and then you have to model that information using the equations and then come to some sort of answer about a specific value. Usually what you want to do is start with the equations which have the least variables. So that's going to be the period, the frequency, the acceleration. All those ones have the least values. So from there you can kind of construct the equation and get more and more variables to get up to the sine and cos functions or the velocity function. So these are the main properties of simple harmonic motion. These are really useful to know if your question asks you to find, the velocity at, half of the end point, or, the velocity at the maximum acceleration or something like that, where you need to understand where the maximum velocity, maximum acceleration, and where they're also zero equal. So at the endpoints, at A or negative A, the velocity is zero. The reason for that is because the object has moved in one direction, and at the endpoint it stops moving in that direction and turns around and moves back in the opposite direction. Another way to think about it is similar to projectile motion. When say it's like a cricket ball or something, is moving upwards and it gets to its maximum height, it stops traveling upwards and starts traveling downwards again. So because it's changing direction, the velocity is zero. The acceleration is in the opposite direction to displacement. And at the center of motion, amplitude is zero. The maximum speed, and therefore maximum and minimum velocity, occur at the center of motion. So the reason for that is, as an object is moving further and further away from its equilibrium, it's like slowing down more and more because it's being pulled back towards the center. But when it's getting back to the center, it goes the fastest that it possibly can. If you just think intuitively about a pendulum, it's going to go slow, and then get slower and slower and slower again as it reaches the end point, and then gets faster and faster and faster again as it reaches the center. The magnitude of the acceleration is maximized at the end points. And the reason for that is because at the end points, that's when the velocity is changing the most. Okay, so if the center of motion of the object is not at x equals 0, then we can use the following equations when x is equal to x0. So these are kind of just ways of making the model, which I guess are intuitive, and you shouldn't have to use too often. Okay, so my tips for simple harmonic motion is, when you're considering it to use sine or cos, try to make the initial phase shift 0. So if the particle starts at the positive extreme of its motion, use cos, obviously, because cos starts at the maximum point, and then the negative of that if it's a negative extreme. If the particle starts at the middle of its motion with positive velocity, then use positive sign or negative sign if it's negative velocity initially. If it starts anywhere else, then you'll need to use a phase shift, depending on, sine or cos probably doesn't matter, and then substitute the boundary conditions to find A and alpha. Okay, so the summary of the motion, is to find the net force. You need to find the sum of all the forces acting on an object, and you'll usually have to use the possibly different vectors and vector addition. You might even have to use like cos and sine rules, stuff like that, to find the net force. Always draw a force diagram. It always makes it easier. Resolve into horizontal and vertical components, rotating the axes if you need to. So if there's an object on a ramp, then you need to rotate the axes. Using those acceleration formulas, so if a is in terms of x, use that formula there to get v squared in terms of x. And then if a is in terms of v, use v dv dx or dv dt to get x over t in terms of v. Simple harmonic motion, the concept is a little bit more difficult to understand, but usually the questions for that aren't too difficult. I would say the most difficult questions are usually to do with those acceleration and velocity formulas up there. So it's probably worth more so practicing those. Okay. Again, I can't go through these questions with you, which I'm very sorry about. But they are in the slides which are available on the website, so have a look at those, and then the answers are also available if you wanted to check those too. So now we are getting onto statistics. So a sample mean, which is a little bit different to what we're doing in methods. In methods, we are finding the mean of a whole population, more so. But in specialist, we are taking a lot of different samples and then finding the mean of each of those samples. So n here equals sample size, just like it does in methods. The assumptions that we have to make is that the samples are independent of one another. That x1 has no effect on x2, and then therefore, other samples don't affect other samples. The other assumption is that samples are identically distributed. So if there's an underlying distribution behind each sample, such as like normal or binomial, then these distributions are the same. So, mean and standard deviation. It's a little bit changed up for specialists. So for specialists, we're not just considering the mean and standard deviation of the population. In specialists, we have the mean and standard deviation of samples and also the population, and they're denoted using different symbols. So here we have that mu is equal to mean and sigma is the standard deviation. So if we just do a quick simulation to demonstrate to you kind of what I'm talking about, suppose that a population consists entirely of the numbers 0 and 1. So half of the population is 0, half the population is 1. Thus the population mean is 0.5. What would happen if we take samples of increasing size from this population? So the real question is, what would you expect if we increase the sample size? How will that change the results? Will that make them more accurate, because you're taking more samples? So this is the results of the simulation. As you can see, the sample size increases as we go along. And what do you notice about the data? Which is that it gets more spread out and it gets smoother. So as you can see in the first simulation, the results are just one big rectangle, but as we get more and more samples, the results spread out more, and they also smooth out more because there's like, you know, more values to fill in each gap. And the other thing to notice is that as sample size increases, the curve approximates a normal curve more and more, which is something we'll get onto. So, the central limit theorem states that, in general, as n increases, the distribution should resemble the normal distribution, regardless of what the population distribution initially looks like. So as n becomes larger, we have a better approximation, which again makes sense intuitively. If you have more samples, your results are going to be more accurate. The properties of the sample mean are that the mean of the sample is the same as the population mean, which is something important to remember, and that the standard deviation is the population mean divided by the square root of n. And something to look at about the standard deviation formula is that as n increases, we're dividing the standard deviation of the population by a bigger and bigger number. So obviously when you're dividing something by a bigger and bigger number, the number that you're going to be left with is smaller and smaller because you're dividing into more and more pieces. So what that implies then is that as n increases, the standard deviation of a sample is going to decrease, meaning that it is, you know, more accurate. So this can be seen here as well. As more samples are taken for each shape, they resemble the normal curve more and more. So this is another way to state the central limit theorem, which is also related to the z-score, and I believe that's on the formula sheet. And it is also important to remember that the central limit theorem, or the fact that you can assume that a population is normally distributed, only applies if n is greater than or equal to 30. I think there was a question about that on my external last year, so I would remember that n has to be greater than or equal to 30. The difference between capital X and capital X dash. So capital X is a single element chosen at random from the population. It's just like one part. And the distribution of X is a distribution of the whole population and has parameters mean, mu, and standard deviation, of which is the standard deviation of the population. So the parameters are the same as that for the population, but X dash is for the sample itself. So it has a mean of the population, but it has a standard deviation of the population standard deviation divided by root n. So a quick computer simulation is I've done here. I'm going to explain all the maths behind it because you can just look at the results. And this kind of just shows how the standard deviation of the sample means gets very close to the standard deviation of the population. Okay, so a summary of sample means. So X is a random variable with mean mu and standard deviation sigma. The sample mean x hat is a random variable whose value varies between samples. The sampling distribution is a representation of all possible sample means and how likely each value is. The parameters of the sampling distribution are the mean is mu, so the mean is that of the population, and the standard deviation of the sample is the standard deviation of the population divided by root of the number of trials. As n gets larger, the sampling distribution resembles a normal distribution, regardless of what it initially looks like, and the approximate standard normality for larger sample sizes is 0, 1. Okay, confidence intervals. So we'll quickly go over interval estimates, confidence intervals, and interpretation of confidence intervals. So, the interval estimate of a range of values for a statistic is different to a point estimate. So a point estimate is saying what's the probability of this exact occurrence, and an interval estimate is saying what's the probability of the value lying between these two limits. So we don't typically use interval estimates for continuous random variables because the probability of like a specific number occurring is like basically just nothing. We typically use interval estimates for continuous random variables, and then maybe more so point estimates for binomial distributions. So, like in this example, if we take a sample of 100 students and find that 60 own a laptop, the point estimate, estimating the whole population tends to be unreliable because it's so specific. So we can use an interval estimate instead and then calculate a confidence interval to kind of show how confident we are in that interval. So in the previous experiment, we might say that we're 95% confident that between 55 and 65% of Year 12 students own a laptop. So basically what we're saying there is that 95% of values are going to fall between that range, 55 and 65%. So the next question is, how are we going to determine our confidence interval? This is the formula that we have in Specialist. It's a little bit different to methods, obviously, because we're working with sample means, not just population means. So we're typically going to use the sample mean and number of trials to find the standard deviation, and then where Z is the quantile of the normal distribution that we're considering. The quantiles, you don't typically have to remember all of the ones here. You usually only have to remember the 95th, 97.5, and 99th. Yeah, you probably don't even need to remember them to that specific decimal place. And then obviously the confidence intervals and quantiles don't exactly line up because the confidence interval is around the center, whereas the quantile like spans over the whole PDF, if that makes sense. I would draw it for you again, but I can't. But the most common one is the 95th confidence interval, where Z is just approximately 2. So as I was talking about for here, the confidence interval relates to the area under the curve. So a 95% confidence interval is where the bounds of the function are such that the area between those bounds is 0.95. Obviously, because the area under the entire function is 1, because it's a PDF probability. And then the endpoints are going to be symmetrical, equally distributed. They're going to have the same area, and they're going to just be like the leftovers of the confidence interval. We can calculate the width of the interval by subtracting the endpoint values from each other, and the margin of error is Z multiplied by the standard deviation over root n. I'll just quickly go over the summary. So an interval estimate is a range of values for the statistic instead of just like a particular one. Confidence intervals are interval estimates with a level of confidence attached, saying like how likely it is that any value for that range is going to fall within your given interval. The confidence interval formula, that one is on your formula sheet, so don't worry about remembering it. The Z score correlates to the desired quantile to calculate, and you will probably need to remember the basic ones for those, which I have down the bottom there. The most common one is a 95% confidence interval, which is when Z is approximately 2. And then the width of the interval is 2ZS on root n, and the margin of error is ZS on root n. Okay. That is it. Good luck, everybody, on your exams. I know that you'll do really well. I don't think we'll have any questions in the slider, but I'll just check quickly. Yeah, so we had one question about tips for related rates questions and finding hard to get the formulas right. Okay, for those ones, as I said before, what I would consider doing is, write down the formulas on your formula sheet, write down the properties of the shape that you're working with, make sure that you're considering what rate you actually need, and expressing that in terms of like a differential equation. What rate you actually need, and then writing the chain rule to get that. So say you need like dH dx, and you've been given dH dt, then you would obviously need to find the correlating rate that would cancel it out and give you what you needed to find. So once you have that information and you think about, well, maybe I need a relationship between x and t, then you can kind of think about the formulas that you've written down and the properties of the shape that you've written down and come up with something for x and t. Other than that, I would really just recommend practicing, do the worked examples, and then work your way up to the harder questions. If you can, find questions on, find questions not just in your textbook but in other textbooks too. Have a look on maybe Khan Academy or something like that. And just like Google them sometimes helps. You can also look at the VCE for like Victoria. Look at their practice exams or the WA practice exams, stuff like that to practice with. But yeah, after the basic structure, just try to practice. And once you've gotten enough practice done, you'll develop a sense of intuition about how to do them. Okay. Well, it's been lovely talking to you guys today. I hope that everything today has really helped you guys, and that you guys do really well in your exams. I know it can be stressful, but don't worry too much about it. If you practice enough and just keep a cool head and you don't get too stressed, you'll be fine. But yeah, thank you so much, and have a good rest of your day.